Afternoon. Thank you for standing by, and welcome to the Minden Dialogue Technical Subcommittee conference call. All lines have been placed on mute to prevent any background noise. Please press star, then the number 1 on your telephone keypad. If you would like to withdraw your question, press the pound key. Thank you. David Gray, you may begin your conference.
Thank you, operator. We sure do appreciate it. Thanks, everyone, for joining us today. I'm going to quickly turn it over to Doug so that he can walk everybody through how we're going to run the program. Doug, you there?
I'm here.
Great.
Okay. Thank you, David, and welcome, everyone. Just so everyone understands, we're in a kind of a slightly different format here so that we're not all live speaking during the presentation. So everyone on the phone who's a participant in the dialogue will have to hit star 1 when we call for questions, and you'll get queued up, and the operator will bring you on to ask questions of the vendor as that happens. Most of you on the participants on the dialogue saw information on this over the course of the weekend, but just to kind of bring folks up to speed, we sent out invitations to approximately 28 different firms. We heard from 13 or 14 firms. Total, some firms, there's one group of firms that are proposing together, and so there's about 4 firms that are on the CH2M Hill list, and a number of others that you'll see on the list that I sent you. The preliminary list this morning had CH2M Hill and Unirem on today's schedule. Both have asked to be moved to tomorrow's schedule. So, and I will send out an email about this shortly. Unfortunately, about a half an hour ago, my email system went down, and I can't send emails. I'm receiving but not sending. So I have to sort that out, and then I'll get all this information to you. So right now, this is our schedule. Today we have 2 presentations scheduled. At 1 o'clock, we will open it up for the CO2AL technology firm that's on the screen. You see their slides here. That's an exothermic anoxic molten alloy process, which I'm sure they will describe. And then at 1:30, we'll do U.S. demo, and then that will be it for today. Tomorrow we have 6 scheduled. Well, actually 6 firms and 7 technologies. We have the CH2M Hill thermal treatment tunnel furnace at 10:30. We're going to do Unirem, their neutralization process at 11. At 11:30, it's Aton, their microwave incineration and oxidation. At 12, it will be Clean Harbor Environmental Services. They have a high-efficiency thermal oxidation system they're going to present. At 12:30, it's going to be Arctech, and they have their Acto Demo non-thermal humic acid process. At 1 o'clock, it'll be Eldorado Equipment talking about their contained burn indoors. And at 1:30, Eldorado will talk about a rotary kiln explosive waste incinerator. You did not need to write any of that down. I will send you the list and the times and everything else as an update tomorrow. So this is going to go fairly quickly as we go through these processes. I'm going to try to keep it moving on the half hour. It'll end up being somewhat abrupt. I'll be ending one and starting another as we move through this process. They'll only have a half an hour. We've left it up to the vendors themselves to determine how they want to use their half hour. I've encouraged them all to leave time for questions and answers. I've also told them all that we'll leave it open for stakeholders to ask additional questions after the presentation via email, and we'll be sharing email addresses for each of the firms for that purpose. With that, I think we can move into this, and I'll sort of talk about how it will go before each one, but essentially when it's time for Q&A, I'll open that up. I'll remind you to press star 1, and we'll take the calls in order. Is Ron Presswood on the call, David?
He is, and we're just moving them over on the speaker side, and so Mr. Presswood should be available as soon as he can speak up and confirm he's on the line.
Yeah, we're here.
Okay, great.
Thank you, Ron.
So it's myself and Ian Bishop.
So Ron, Ian, welcome, and thank you for joining us and taking the time to do this. It is a strict 30-minute presentation, so at 1:30, I'll give you some countdown times, but at 1:30 I will absolutely close this down so we can be fair to the next group so that they have enough time moving forward. So your phones will go down and theirs will come up. I'll give you sort of the halfway and a 5-minute warning. When you are ready for questions, just note that, and then we'll turn the operator on to bring up folks who have questions. As I said in our correspondence, I do encourage you to leave a little bit of time in your 30 minutes at least to answer questions for folks. How you want to use your time is up to you. I will turn it over to you now to start.
Hey, Doug, this is David.
Yeah.
Just before you do that, would you let them know how you're going to move through their slides? They need a prompt you to go to each slide.
I'm sorry, you don't have control over your slides, so I'm going to move your slides. You just say next slide, and I'll move it forward.
Okay. So our slides are pretty short. We wanted to leave as much time for questions as possible. So if you'll go to the first slide. So what our solution does is we can eliminate and recycle the M6. We do it using a molten alloy bath. Now we have a patent on the process for greenhouse gas. We've done some preliminary work with doing coal as well. So we've been able to run coal through the process, specifically lignite coal, and running the coal through the process, what we ended up seeing is we broke it down and we were able to get carbon, sulfur, and then different length or hydrocarbons, so all the way from short chain to mid chain hydrocarbons. So similarity in that N6 has, you look at the MSDS sheet, it has an ignition temperature of 383 degrees. The lignite coal is right in the range at 400. So, powdered the lignite coal, ran it through our process, and again, it broke it all down. Again, running the coal through the process, it was very simple, and so we have a machine design based on that, and that's a project we're trying to fund right now. The specification you had was for M6 and for CBI. We did find an MSDS sheet for CBI, but it's not very clear on the material itself. But looking through it, we think we'll get elemental material, aluminum and aluminum salts. But we would ask for additional information on the CBI before we could actually give you a specification on what we're going to do there. If you'll go to the next slide. So these are the chemical compositions that we picked up for the M6 off of the MSDS sheets. Everything you see in red is actually the compounds that are listed in that MSDS sheet. So running it through the bath and looking specifically at aluminum, what you'll see on the right-hand side, your typical stoichiometric equation, is what we actually get out. So, you look at the nitrocellulose, which is the primary ingredient in N6, you can see we got carbon, hydrogen, nitrogen, and alumina, which the alumina comes off and we're able to recycle. And then if you want to go to the next slide, it's an actual schematic of the machine. So what we do is, depending on what compounds are going to go into the bath, we actually create an alloy. So it's primarily aluminum, but then we can add other metals in it to facilitate the actual process. So The bath itself is enclosed. It has a nitrogen atmosphere. There's no oxygen in it at all, which prevents any pyrolytic processes from occurring within the bath. The aluminum is, and some of the other compounds are scavengers for oxygen. So for coal, when we put it in, that facilitates the breakdown of the compound because it's the aluminum and one of the other alloys that we put in actually scavenges for that oxygen molecule. And when that happens, then you see a breakdown. It's an exothermic process, so we create heat. That heat can come off. We can either do a cogen process or we just run it through a heat exchanger and dump the heat. But then what comes off, the gas, the nitrogen gas that comes off that we drive the process with, runs through, and then we can take off the carbon, the sulfur, run it through a cryo unit, and we get hydrogen gas, and then we recycle nitrogen that comes off back through the process to actually drive the material into the bath. So that's all shown within that schematic there. The last slide is actually just in my contact information. But if you'll say it, that one is process design. We know you have questions, and that's what we're here to answer the questions. So if you want to open it up, we're ready for questions, unless Ian has something else.
Well, I mean, basically what this comes down to is, the problem was, as we understood it, the problem was the burning. And this process, we just get back to all the original elements, or as close as possible to the original elements as we can. So there is no burning, there is nothing to landfill, unless you want to landfill elemental products, such as the sulfur or the carbon. The aluminum is the third most recycled product on the planet, so that gets recycled. So we thought this was a pretty good option as far as having no environmental or causing no environmental harm, such as the people in Minden did not want the burning. So that's what we were thinking there as far as it goes. On the slide of the chemical composition, you see that you get the carbon, you get the hydrogens, you get the nitrogen coming off. Nothing harmful is coming off. So if there,
okay.
It's a simple process. We've been working on this for a number of years, and we know it works.
And one other point I guess you made is this work the original development work was done at the University of Houston. Once we got through that, and then we sent it, and it actually was peer reviewed at the University of Texas in Arlington. And we have that information too, if you'd like to see it.
So great, thank you. Let me just remind folks to press *1 on their phones, and including participants in the dialogue committee. You're all in the public place right now, so the operator will bring you in turn as you press *1.
And your first question comes from the line of Slavomir Lobnicki.
Hello. I have two questions, actually. You mentioned in one of the previous slides that you are using aluminum salts, among others, and I would like what kind of salts are those, if there is any aluminum chloride or any other chlorine source present in the system.
Actually, the aluminum salts are an offtake. So if you have a compound that has chlorine in it, the aluminum actually will scavenge that chlorine and will create that. So that's a byproduct. With the chemicals or the compounds that we're talking about here, since there's no chloride, we wouldn't see those salts. That is a possibility with the CBI. There's iodine, there's a chlorine in there as well. I can't remember what the compound is right now, but we would see that we would get salts in breaking the CBI down.
Okay, and I understand that steam is a product of your process, right?
We use water to cool the machine because it's an exothermic process. So we can generate steam, and that steam can be used for cogen, or we would just have to dump the heat. We'd run it through a heat exchanger.
Okay, thank you.
You're welcome.
Your
Question,
next
please.
question comes from the line of Dr. Brian Salvatore.
Yes, hi. Good afternoon. Yes, I enjoyed looking at your process. I'm a chemist, and I think it is a clever idea. And so I have a couple of questions for you. One of them has to do with your energy source. So you're talking about using the lignite coal, and we do have a lot of that. Of course, our SWEPCO plants around here do make use of that, but it does generate a lot of mercury. And in fact, there is a SWEPCO plant over there in East Texas which is not properly scrubbing. They are in trouble with the EPA right now, and they're fighting the EPA until they absolutely have to put these scrubbers on. But the mercury limits already here in Shreveport are up in excess of what they should be according to EPA standards. And I'm just concerned about another large operation in this region which is making use of that lignite. And I wondered if you could say anything about how you would intend to really subscribe to the EPA's scrubbing standards that are today, not 20 or 30 years ago. There's technology to do that. So that's my first question.
Okay. Well, actually, we were using the process to actually gasify lignite coal. The reason why we brought it up is because that molecule in the process is somewhat similar to what we're talking about with the M6. The heat source that we use is actually to initially melt the alloy pool as natural gas, and then once the pool is created and we start processing material, it's exothermic. So we're actually, once you get it up and running, we don't have to add in any additional heat. But to your point of mercury capture, that's part of the reason why we've been looking at coal, because we capture the heavy metals, the sulfurs, and all the secondary products that would come off from gasifying coal.
Okay. And you could do that with lignite too, right?
Yeah, we do it with lignite. We've actually demonstrated lignite.
Okay.
And on the process design, you will see the floor of the vessel, and you'll see an offtake at the bottom. That's where the mercury and the heavy metals are taken off.
So that would be slide 3.
Be slide 3, yeah.
And the carbon is taken off on top?
Actually, the carbon comes off as a powder. It's elemental. So it's more of a dust, which is then captured in the bag plant, and that would be the same with the sulfur. It's actually entrained in the nitrogen that we use to drive the system.
Yeah, okay. And in terms of the scale-up of your process, I know it's been tested and I know it works, but we're talking about here 20% of all the demilitarized propellant in the entire country. How confident are you that it could be scaled up and work on that scale? Since it is it's a new idea, it's a clever idea, but what about the scale-up?
We, again, looking back to the lignite, and the greenhouse gas process, so we did the base research at U of H, and we started off doing TGA with the TGA. We did that. We moved up and did a larger sample, and we've done up to 20 kilograms. And the chemistry and the thermodynamics have held at each step. There's a local manufacturer of smelting machines, and we've talked to them about machine designs. So we have several different machine designs. So in varying sizes depending on flow rates. So, all we would need to do is figure out, what treatment, what input flow rate you're talking about. How much material do we want to put in and treat at a given time. Our desire is to run this 24 hours a day, 7 days a week. That way we don't have to cool the pool. And then, at the end of the day, it would cool, and then we'd have to reheat it. It's better to keep running it on an exothermic basis. So went and had a conversation with, I'm a mechanical engineer, and we went and talked to the professor at U of H about the applicability of doing this, and he didn't see any issues with us being able to treat the material.
Thank you.
Your next question comes from the line of Karen Price.
Yes, I'd like to know, in preparation of this, how would you be able to prevent an excess exothermic reaction?
You mean, are you concerned about the material igniting before it gets in the machine?
Yes, sir, before it gets in the machine and when it's placed in the bath.
Yeah, the way the material, and again, it's an issue with coal as well. The bath runs about 600 degrees C. So, we had to get the coal into the machine. So the sparge tube is actually cooled, so it has a heat jacket on it. And then the nitrogen that we use to drive the material into the bath is cooled as well. It's atmospheric temperature. So as you drive it in, that actually pushes the material into the bath and gets it into the pool. So you don't have, you're not worried about it igniting in that tube before it gets in. Now, if it was to ignite in the sparge tube, what would happen is you would, it's still going to get pushed into the bath, and as soon as it gets in the bath, the aluminum would start breaking down any of there would be CO2, CO2, or any compounds. Those would break down in the bath, and the heat would get absorbed in the bath itself. And then you would see a scavenging of the oxygen molecules of whatever solid was left.
Okay.
You do realize, of course, that the M6 product supplies its own oxygen.
Yes.
And that its main purpose as a propellant is to create a CO2 molecule.
Right.
Can you just identify who was just speaking, please?
That's Kermit Wittenberg. He's works with me, Karen Price. That's
fine. I just wanted people to know.
Yeah, if you go back to slide 3, which is the chemical composition, you'll see that, the nitrocellulose, again, is the major constituent, and it has all those oxygen molecules on it. So that's what you're talking about, is that when it burns, that's contributing its own oxygen to into the reaction. And the bath that we have actually wants aluminum, and 2 of the alloys that are going to be in there actually want that oxygen molecule. So you get that reaction, and as soon as the reaction occurs where you create the alumina, which is a ceramic, that carbon can't take, and it's no longer going to be self-reactant because that oxygen molecule has been bound up, and it's no longer available for the nitrocellulose or any other compound to consume or for those carbon molecules. So the original material is not going to have the chance to oxidize any further.
Okay, I didn't hear earlier an answer to what fuel source that you're using on this process.
We use natural gas to start the process to melt the aluminum. Once the aluminum we've created the molten pool, in the reaction of it breaking down these compounds and creating the alumina, it's exothermic, so it creates its own energy. Actually, we create enough energy that we can run a cogeneration process, or if there would be some other process out there that needed heat, we could provide heat to that process, or we just run a heat exchanger.
Next question was, and also in the preparation, you talk about the blowing the material in. You talked about grinding the coal. Are you grinding the M6 in preparation?
No, given the size of the material, we should be able to just put it right into the bath.
Is this dry blowing or wet blowing?
Dry. It'd be used nitrogen.
Okay.
We have to grind the coal. Coal comes in big nuggets, and you can't push that through. We don't want those big pieces going in, so we grind coal up to get it like pea gravel sized piece to add to inject into the bath.
Okay, and can you just tell me real quick, when you say you've done D-mill, can you identify where you've done that?
I'm sorry, we've done
your D-mill. It indicates you have experience with demilitarization of propellants and explosives.
No, we have no. This is the first time we've looked at something like this. We've done greenhouse gases, VOCs, coal, which again is somewhat similar in the temperature range that it wants to ignite at. But we have not done anything with material like this. Now, taking the MSDS sheets and the material that we've been provided, we did go to the University of Houston and sat down with the professor to talk through what could be potential issues with the process, and we could not come up with anything that we saw would be a showstopper.
Okay, thank you.
Those all your questions, Karen?
That's all my questions.
Thank you.
Your next question comes from the line of Mickey Walsh.
Hello, I had a question. Can you hear me?
Yes.
I had a question for you as how long it would take to build the equipment necessary to be able to do this process.
2 to 4 months.
And then how long would it take for you to complete the demilitarization of the 16 million pounds?
Again, that would be based on the flow rates that we'd be looking at. To be honest with you, we haven't sat down and done those numbers.
Okay, and then let me ask one more thing. How do you deal with the handling of the M6? It's in a fairly unstable state, and trying to get it to the equipment would be a big concern.
That would be something that we would like to have some guidance from. You'll have a lot more experience at that than I.
Okay. And I got one other item I was curious about is what happens to the DNT that's in the product?
I'm sorry, the what?
The DNT, dinitrotoluene. Was that explained in your?
Yeah, that would be on slide 3, and because it's essentially carbon, hydrogen, nitrogen, and oxygen. And when you strip that oxygen molecule off, it breaks down. So then what you end up getting is carbon, hydrogen, and nitrogen. And the nitrogen we use to drive the process.
Okay. That's all the questions I have. Thank you.
Thanks, Mickey.
And we do have a follow-up question from the line of Slavo Lomnicki.
Some follow-up questions based on what you talked about already. So 4 questions, actually. First of all, what is the overall alumina amount that you need to use per unit mass of the material to be destroyed? Do you have any idea?
Yeah, we did a base calculation, and we think it's going to be about a half a pound.
Per pound?
Per pound, yes.
Okay. Now, the second question is on your scheme. It shows that alumina slag is one of the wastes.
Well, yeah, alumina comes off, but then alumina, because it comes right off, it actually ends up being less dense, so it floats to the surface. And
but I mentioned it wouldn't be a clean alumina. It would be contaminated with a lot of organics on it.
No, actually because there's no, again, by what we've been given, everything we see is either carbon, hydrogen, nitrogen, and oxygen. So coming out of the machine, there shouldn't be any other organics. It would just be alumina.
What's the actual temperature of the process?
It runs anywhere from 600 to 900 degrees C.
So I can tell you that at this temperature, you won't have a complete destruction of aromatics.
Are there what aromatics? We haven't seen anything that shows there are any aromatics, but I can tell you from experience we have been able to break down aromatics.
Well, I know that you will, but not completely. There will be some left over.
Well, then that would, because we would run that back through the system, and given residency time, those aromatics actually break down. We've had experience with some other aromatic compounds, and we've seen that they've broken down.
Okay, but you haven't done any actual testing of your waste alumina stream. Let's put it a different way. Any waste alumina stream, is there anything left, or you put everything back into the process?
The alumina we've taken, the alumina that we've taken off, we've just used for analysis purposes to calculate, to verify the thermo and the chemistry to make sure that our analysis has been correct. We've actually not taken the alumina and done any analysis to see what, if anything, other than alumina would be in that mass.
Okay, and you're not feeding it back to the system, right?
Not the alumina, no. The alumina is an offtake. We look to put back in the market.
And what's the yield per pound, let's say, of this waste stream?
The alumina?
Right.
You get 2 pounds of alumina for each pound of aluminum consumed.
Okay. So per 1 pound of waste fed to the system, you're getting 2 pounds of this alumina sludge, right?
You would get 1 pound. It uses about a half a pound of aluminum, and then you get 2 pounds. So that would make a pound of alumina.
Okay. So
if there's additional, when you look at that chemical composition, that's what we did our analysis on. If there's more compounds than that other than what you see on that one slide, if you'll let me see it, we can work through that and tell you exactly what we would be expecting.
Okay. Let me break in here for 1 second. We only have a few minutes left. Operator, are there other people on the line?
Not in queue.
Okay. So, Slavo, you'll have the last question.
Can I still ask a question?
Yes, go ahead.
Okay.
We have one more.
Two last questions left. So how long, because I understand it's a batch process, so how long it takes for a normal batch to finish?
It's not. It's a continuous feed.
Oh, it's a continuous feed. Okay.
Yeah.
And the last question is, from your diagram, all the carbon is actually being converted to fine powder, and it's probably a super fine powder, very small diameter size. So
actually not. Go ahead. I'm sorry.
So have you done any testing of your capturing efficiency of this carbon, if there is any potential of emission of this powdered carbon?
Well, so far we've captured 100% of the carbon, because it doesn't come off as a fine dusty powder. It comes off, and it's interesting the way it comes off, because it doesn't come off as little balls. It actually comes off as what would look like chains, so it's fairly easy to capture. And the sulfur comes off as again, it's not a fine powder. It's more of a particulate size, so it's fairly easy to capture.
Okay, that's all of my questions.
And I guess the last thing is, we would have a filter in line before it went into the cryogenic unit. If we're going to try to capture the hydrogen gas, we would have a filter that would be a pre-filter to make sure that we weren't running any fines into that cryo. But again, it's a closed loop, so if there were fine particles, they're not going to get blown out into the air. It circulates back in and will be blown back through the bath.
Okay, thank you, everybody. We're going to have a
Hey,
short...
Doug.
Yeah.
Doug, I'm sorry to interrupt you, but I just got a note that Frances was having trouble having us activate her microphone. Could we take a moment for one question from her?
We can. David, could you handle that? Because I've got the other people that are having trouble getting in. I need to call them.
Great. So operator, if you could do me a favor and open Frances Kelly's microphone, please, and reopen our presenters' microphones. We'll ask Frances to present a question also.
Frances' line is open.
Okay. So what I think I heard you say was that you have the capacity to do hold, test, and release. Is that correct?
I'm sorry, hold, test, and release?
Right. So anything that would be coming off of this, any waste stream, whether it's the things that are coming off the bottom or the carbon or the gas, you would test to make sure that there would be nothing dangerous in that.
Correct.
Okay. And would you be testing for the organic compounds?
Again, I don't have any information on what organic compounds that we're talking about, because
there are organic compounds in the M6, and what we're understanding from your process is that the aluminum pulls the oxygen off of them and breaks them down, but there's never 100% destruction efficiency, and there could also be byproducts created, and so that would be a question we would like y'all to follow up in answering to us, is how you would be able to test for any organic compounds from the source material or that could be created during this process before anything is released.
Yeah, that'd be easy. We can design the system to check that nitrogen, the nitrogen gas we release, to make sure that there's nothing entrained in it. And we can also check any of the solids that come out as well. We do have a lot of experience with testing of different, again, we did the coal, but we've done other compounds, specifically VOCs, with the idea of you get VOCs entrained from gas electrical plants that are burning coal, those greenhouse gases, and we've either broken down all the greenhouse gases or the VOCs, captured the heavy metals and the particulate matter. And so we haven't had, in all the testing we've done, we've had zero off gas other than nitrogen.
Great. Thank you so much. Operator, if you'll go ahead and close down the lines for us and reopen the next set, we'd appreciate it.
Okay. Give me just one moment.
Has anyone from the next group called in?
Yes, David Couch, best email.
Thanks. Sorry for the confusion there.
No problem at all. Just waiting to be called to go.
Great. You're ready, Doug.
Okay, so we're going to transition now to the next group, which is U.S. DMIL, and again, we'll let them do their presentation, and then we'll take any questions for the remainder of the 30 minutes, and you'll need to press the *1 to get in line for those questions. And with that, I'll turn it over. You do not have control of the slides, so just tell me when you want me to move the slides, and I will move them for you.
Understood, sir. Thank you very much. Thank you for allowing us to present today. My name is David Couch. The company name is U.S. DMIL, short for demilitarization. We are a proven, deployable technology for the demilitarization of munitions, munition components, propellants, and explosives. We have experience and performance with Department of Defense and see this as a perfect application for our technology. Second slide, please. Unlike the legacy technologies that have been deployed in the past, decineration produces no byproducts, has no residuals or wastes, has no outside chemicals being added, is not incineration. We are not a combustion process. We do not burn. We do not detonate. There is no flame involved. And we are designed from the beginning to be deployable. The concept is to go to the problem site, not try to transport the problem site all over the country to get to where you happen to be set up. Third slide, please. Decineration technology has been proven to be licensable, permitted, if you will, in any state, country that follows U.S. EPA regulations. We have proven by analysis of our gases that we can meet the current new MAC standards, not be grandfathered and not be locked to asking for waivers or permissions. We can meet the MAC standards. As I said, we're non-incinerative and have been recognized by the U.S. EPA headquarters Solid Waste Division as a recycling, disassembly, reclamation, and other material process. Doesn't sound like much, but it does mean in a munitions exemption rule state that we are not considered under RCRA. But it does also mean that we can apply for and have applied for our permitting and gotten it in the state of Utah, for example, in the minimum time allowed by their regulations. Basically what decineration does is we are breaking the long chain hydrocarbons in the solid energetics, nitrocellulose, nitramines, nitroesters, and decomposing them into shorter chain hydrocarbons that are then removed from the vessel and treated before expending out to the atmosphere. Process occurs furnace temperatures of approximately 400 to 900 degrees Fahrenheit. I'm old school, so I use Fahrenheit. I apologize. But that is the temperature, and what we're trying to do is hold the temperature of the energetics at around 400 to 450 degrees Fahrenheit. If we could go to the fourth slide, please. Basically, this is a mature technology, and I can't stress that enough. This is not something that has just come out of the laboratory. It is the basis for making gasoline from crude oil. It is the basis in I come from Allied Chemical. It's things that we did routinely. What U.S. Steel Mill has done is taken mature, proven technologies that are commonplace in certain industries and bring them to the demilitarization community where they've never been seen before, and we've been very successful. Primarily, if you look at the bottom, what we're doing is the nitrocellulose is a very long-chain hydrocarbon. We're adding enough energy to start breaking the carbon-carbon bonds, some carbon-nitrogen, some nitrogen-oxygen bonds. At that point, when the solid material has now broken and is a shorter chain hydrocarbon, it leaves the hot plate model of the inside of the furnace. There's a vapor state. We pull it out. We treat it in our air abatement system. Our air abatement system, again, proven technologies. It's a water scrubber followed by a catalytic converter. And the beds in the converter are specifically designed for the destruction of TOVs and any NOx that might form. Either form, not really form, but when we break the nitrocellulose, we're not always sure which molecule bond is breaking. So some NOx is simply there because that's what happens. Those are the bonds that break. But what comes out at the end of our stack is CO2, nitrogen gas, water vapor, just the same as comes out the tailpipe of an automobile after it's gone through the catalytic converter under the car. We don't have any added materials that have to be added to the feed in order to process. We don't have any residual waste that are left behind. Again, we're not burning or detonating it, and it's a process that has been proven under a federal contract. We are designed specifically and exclusively for processing munitions, explosives, and propellants. So again, we feel that the concept of handling, feeding, and processing the material is understood by us and our team. And then the fourth screen is simply the contact information. And again, what you're seeing in the picture is our unit deployed on a federal installation where we were processing munitions. I know a lot of people say, well, the munition is not always exactly like the propellant by itself. All the munitions that we were processing contained propellant, maybe not M6, but it is still, in essence, nitrocellulose with the nitrotoluene and the other modifiers added. And again, we're not trying to burn or form combustion in the furnace. That's the last thing we want. What we're doing is making a solid-state long-chain hydrocarbon into some sort of a broken chain so that it vaporizes, and then we treat it, the gas, if you will, in the air abatement system. So for the citizens of Louisiana, what we're doing is a permittable, deployable unit that can show up at Camp Minden. We're electric, so we're not pulling natural gas. We're not pulling fuel oil or any other hydrocarbon source. We are not an incinerator by the definition of the U.S. EPA. So I guess rather than hammer on what I think needs to be said, I'll ask to open up the telephones for questions coming in.
All right, thank you, David. Operator?
At this time, I would like to remind everyone, in order to ask a question, please press star 1 on your telephone keypad. Press star 1 to ask a question. And your first question comes from the line of Samuel Mims.
Good afternoon, whatever it is. I have one question. I'm not a scientist by any stretch the imagination, but I am deeply concerned about what comes out of this thing and in what quantities does it come out. So I can see CO2 and nitrogen, and I can see the water. And you say it's the same as what comes out of the from a car which has a catalytic converter. So my question is how are you able to measure the amount that comes out, and to what degree of efficiency are you able to measure that, and where do you measure it at?
To answer the question, we had a full continuous emission monitoring system on us, and I have to refer to our previous runs where that kind of data was collected on a real-time basis to be supplied to the Department of Environmental Quality in the state of Utah. The amount of carbon dioxide and the emissions products are based completely on the chemistry of what's being fed in. So on a nitrocellulose, which has 17 carbons, we're going to put out 17 pieces of CO2 because we have to balance the carbon. But what we do not do is add any further load to the environment by consuming gas, oil, coal as our energy driver. But as in any permitted, regulated operation, there would be an emissions monitoring system where we have the ability in real time to calculate how much. Primarily, they're more worried about carbon monoxide, CO, than they are CO2. But these are all things that can be monitored real time and reported as things go forward. So I hope I've answered.
Okay, thank you.
Thank you, sir.
And your next question comes from the line of Slavo Lomnicki.
Before I ask the full question, let me ask you if I understand it correctly. So your first step is generally a pyrolysis system of nitrocellulose, and then the off gases go to the secondary unit, and you just said that this is a off gases abatement process. So what kind of abatement process is it? Is it an afterburner, or what is it?
No, it is a catalytic converter. We do two stages because, again, we are designed for a broad line of munitions, and that's how we've envisioned and engineered and fabricated the machine. The first stage, after coming out of the furnace, the process gas is pulled through a wet scrubber where we can collect any particulate, which would not be expected processing pure propellant, but we can also do some chemistry additions to the solution to help grab certain elements if they're coming through. In the case of the pure propellant, where we see the biggest thing being is to the catalytic converter. What this is actually two separate beds built into a single unit. It's brought up to temperature electrically prior to the start of operations. Then once the vapor is pulled through it, the exothermic release from the decomposition of the hydrocarbons keeps the beds hot. One bed is specifically selected to catalyze hydrocarbons, the other bed specifically to catalyze NOxes. So in the NOx bed, the off gas of that is elemental nitrogen, or nitrogen gas N2, and O2 being released from the recombination. And I apologize, I buy the machine. I am not the chemist, so I can't tell you what specific the catalyst is, other than that I know it works.
That's fine. Now, my question is, so this is good that you explained it because I wasn't sure about it. Now, my question is then, the pyrolytic process of cellulose in general produces a very large amounts of small molecular weight compounds, such as like levoglucosan, hydroxyacetaldehyde, many others, furfurylaldehyde. There's a lot of aldehydes. On top of it, DNT, the major product of the DNT pyrolysis, would be actually toluene.
Yes.
And this will create a quite heavy load of different organics in the gas phase. So the question is, did you measure the efficiency of your catalytic bed?
Yes. To answer your, I'm sorry, sir.
And what's the destruction efficiency then?
The destruction efficiency is 99.9%. I agree with your analysis that, and I appreciate your grasping of it, sir, that we are building a fuel stock. For lack of a better term, we are making a very heavy organic low fuel stock and driving it against a catalytic converter. So compared to some installations where you would see, your physical size relationship between a furnace and the air abatement system, our air abatement system is significantly larger than you might anticipate because it is specifically designed and engineered to handle, in essence, a fuel stock being thrown at it. And this is not a consequence, but it is the intention. We do not intend to burn or combust in our incinerator. We are simply trying to get the propellant, the explosive, to go to a condition that we can drive it against the catalytic converter as a second stage.
No, I understand. Now, my concern is, the number that you just said is that the converter efficiency is only 99.9%. Now, with the amount of, for example, toluene that would be produced, a lot of toluene will escape.
Okay. Again, I'm not the expert. I buy this system, and if this is a concern, and one of the things we would be doing in any deployment, the first thing you do is after you get set up, you run what's called formulation runs, which tells you where to set all the knobs and dials so that you tune it specifically to what you're operating. If it is felt in any point up to that time that the efficiency of the catalytic converter is higher, there is nothing that says we cannot put a secondary bed, tertiary bed, if you will, either internal to the group or after the first catalytic converter, aimed specifically for like a toluene item, specifically one of the heavier organic vapors. To us, it's simply, let's get the job done, and if that means I have to buy a bigger device than I would at a different deployment, that's just what you do.
Okay. And the last question is, you will actually, during the pyrolysis process, of the initial material, you will actually form probably a pretty significant amount of char left over.
By actual proof of operation, no, we don't.
So there is no char left over whatsoever?
What we have had come out of the machines when we are running propellant-containing munitions is the metal, the munitions themselves. We would have pictures, but I did not want to confuse and overpower the system here by dumping a lot of photographs. The propellant, we do not leave a char ash residue, and again, this is documented under DoD contract. that the effect or concern that you're raising does not occur in practical operation of the unit.
Is it a batch process or continuous process?
Continuous. Once we start up the system, the only time we ever shut down is for the demands of the labor pool we're working with or the demands of the contract. We would see something deployed to Camp Minden, set up, turn it on, and not shut it off again until the problem is resolved. Because of a question of scale-up that came up on another caller, I'll say this. The machine, how many machines we would put on site, of course, affects how quickly it can chew through the stockpile. But the more machines you put on site, of course, there's more machines going onto the site. So this is all something that can be discussed further, but the machines themselves run 24 hours, 7 days a week, 365 days a year, and they're not prototypes. They're not something that we actually build. We actually have the premier electric furnace builder in the world make these units for us. They have.
Excuse me, I'm gonna chime in here because we have a lot of people waiting for ask more questions.
Oh, I'm sorry. Go ahead, sir. I didn't realize.
No, that's okay. I just want to make sure we can get to as many as possible.
Okay, thank you.
Operator.
Sorry.
And Francis Kelly, your line is open.
Hi. My question is, do you have the capacity for hold, test, and release?
I'm sorry, repeat. I missed for the capacity to do what?
Hold, test, and release.
For emission.
That means, mm-hmm.
I'm not sure what you mean by the term, ma'am.
Okay, so what I mean by that is any waste, any gas that would come off, any liquid that would come off, any solid that would come off or be a byproduct or end product of your process would be captured and then tested before it would be released into, the atmosphere or anything else. And if you do that, what compounds would you be testing for?
I see. Okay, very good. Sorry, I didn't understand. As I mentioned earlier, in a case of a pure propellant, about the only avenue for release from our system is through the abatement system. That would have on it a continuous emission monitoring system that would meet the requirements, in this case, of the state of Louisiana, US EPA. If they asked us to monitor for, whatever items they ask, opacity, CO content, excess oxygen, whatever it is, that gets worked into the SEMS package, gets picked up and recorded. The solids, if there are any, typically if we're running munitions, we collect them in barrels, hold them for Colossus testing to make sure that all explosives are gone from the items, and then in the case of metals, we sell them off. But if by chance, we're collecting anything solid, of course, we would have that held in barrels and correctly identified and that analyzed and disposed of. We do not use any water, so there would be no liquids coming off of our system.
Okay, so just to follow up on that, in the continuous emissions monitoring, I don't know if you can answer this today, but if you could get it in writing to us, we would definitely appreciate that. Are you able to test for hazardous air pollutants and specifically for organic compounds?
Yes, ma'am. I can tell you that right here, right now. Yes, that is specifically one of the things that can be looked at on a continuous basis.
Can you provide us the information for how you would do that in writing, please?
Yes, ma'am. I will have to get back to, again, I don't build it myself. I would buy it from, again, one of the premier folks in the world that do this. I will get a statement from them and forward it to the committee.
Thank you.
Who should I send it to, Douglas or to?
If you send it to Doug, I'll make sure everybody gets it.
Thank you, sir.
Thank you.
Thank you, ma'am.
And your next question comes from the line of Robert Flournoy.
Is your name David Cox? Are you the one whose name's on the sheet?
Yes, sir. That's me.
You are. Okay. Let me ask you this. When you have some M6 experience, have you had experience with M6?
It has been a propellant inside of munitions that has been processed. I will not say that we have done both. It's just not something that has come up before to process both, but propellant inside of munitions, yes, sir.
Okay. Let me ask you this. Are you approved by the ESB, the Explosive Board?
We have been reviewed by the DDESB. We've had DDSB approves facility installations, not specific machines. In other words, I cannot have my machine installed, say, in Utah, pick it up, set it down in Louisiana, and have that certificate transfer with it. I have to have the site plan with the machine reviewed as it would be installed in Louisiana. It is just one of the courses of doing business, and it would happen. We've had it before. We'll have it again. So I don't want to sound cavalier, but it's also not like a vehicle VIN number. It doesn't travel with the machine.
I got you. We're running out of time. Let me ask you another question real quick.
Sure.
How long would it take to get your stuff here on site on Camp Minden? How long would it take to get the
I have one machine. I have one machine right now that I would just have to pair up with an appropriate air abatement system. So I could have that machine. In other words, again, it's currently available. I can't guarantee its availability. I could have everything deployed with that physically on site in probably about 10 to 12 weeks. The question is the permit. I challenge anybody who says they can walk in and start operating without a permit. You can't. So the critical path on everything will be the permit. We've had success in getting them in 143 days. To me, that's the point at which I can turn the switch and start running. But we would be ready to go.
My last question is, about the residue that needs to be tested? It should be tested periodically rather than waiting until the end of the work. Do you take samples periodically and have those sent to an approved laboratory?
No, because quite honestly, what we would do, and this is the art of the science and not the science. When we're done, probably the first thing we would do, if we did have a barrel of residue that we felt still had some organics, we would reset the temperatures in the furnace, reprocess that to see if we could make whatever that collected residue is go away through the system like we wanted it to before we approached it. But then, of course, we would have it in the barrel. Anything that survived a second run, we would properly analyze and send off. But we don't, I guess I understand, but it's hard to explain. We don't have a fraction of a percent of the weight of the material that goes through the machine come out as a solid form. It truly, truly, truly does go to a gaseous state.
Yeah, it would be nice, and you could put this in writing to us, the laboratories that you use, their qualifications, and so forth, and who their lab director is when you have some of these samples have to be analyzed. Okay, thank you.
Well, thank you, sir.
So, operator, how many people do we have in line?
We have 3 altogether.
Okay, let's try to get through them if we can.
Okay, and your next question comes from the line of Dr. Brian Salvatore.
So I have a question for you about any differences that you would foresee with, first of all, that this is bulk propellant, and what percentage of your actual jobs in the past have been with bulk propellant, and then also the fact that this is not just bulk propellant, but it is bulk M6. And so this is going to be very different from just pure nitrocellulose in that we have about 2 million pounds in there of some semi-volatile organic compounds. And you're operating, you say here, between 400 and 900 degrees Fahrenheit. The boiling point of DNT, for example, is around 550 degrees Fahrenheit. I'm just concerned whether that 99.9% will hold up with these aromatics, with semi-volatile, which could quickly move up your column. I'm concerned about your column perhaps operating as a distillation column for some of these semi-volatile organics, and how would you ensure their complete combustion?
Okay. Again, if I could back up just as a question to clarify, if you're talking about combustion and referring to the...
Yeah, decineration, sorry.
Okay, the decineration, we do not have combustion. What we're avoiding,
right.
What we're actually doing is, if you will, distillation, cracking, hydrocracking in that tube.
Substitute that word, but address my concern.
Okay, very good, sir. Again, this is part of the formulation and the art of the science. Part of the formulation process is to go through, make small runs, multiple runs, to tune the system to handle bulk. The first answer is we have not handled bulk M6. We've done actual true black powder, charcoal, sulfur, saltpeter mix, and we've done modern propellants, and modern to me is from, say, World War I forward. The specific, all modern military munitions, propellants carry stabilizers and modifiers to change how the burn rates and the burn characteristics are. So to us as an engineering group, it's a question more of tuning it to a specific assignment than it is to see a huge difference between M6 and M2 or IMI or any of the more current modern propellants. The breakdown of the nitrotoluenes. The modern double and triple base have nitrotoluene, nitroguanidine as the adders to modify, and we've been processing those successfully. So again, I don't know how to address your concern. We might be running, we can tune the temperature in that tube in 3 separate zones. So we might even say that using, in the practicality of the run, the third zone we might set to 900 degrees Fahrenheit simply to make it that if anything gets back through that far, as you're suggesting, some of the heavier semi-volatiles, they're processed in the third zone, whereas we're getting rid of the vast majority of the nitrocellulose lighter compounds in the first 2 zones. This, again, is part of our tuning process and formulation. We never come forward and say one size fits all, one setting causes all solutions. We're engineers, we're practical. We know that you tune to the application. So I hope I've at least answered a little bit.
Is that your whole question, Brian? Okay, operator, next.
And your next question comes from the line of Mickey Walsh.
Hello, I just have a couple of quick questions for you. You mentioned the destruction efficiency was 99.9, and I was wondering if that's consistent throughout the operation, startup, shutdown, et cetera.
The efficiency was calculated for that particular calculation during a 3-day RADA of the CEMS system out in Utah.
Okay.
What we do in this case with this kind of a workload is we would start it up, and typically it would take about 2 hours from start to the machine to stabilize, and at that point I do not see shutting it off unless labor needs it. I wouldn't force people to work on religious holidays, but other than that, I don't see a real reason to shut down the machine.
What would be
the disruption you're I think is where you're questioning does not occur.
What would be your expectation for handling the munitions that are there now, the 16 million pounds?
I'm not sure what you mean. I'm not sure what you mean by expectation.
The time frame.
Oh, the time frame. Again, as I said earlier, it would depend on whether the project can support more than one machine. I would see 2 machines on ground. I mean, right now, I don't know all my pricing. I would see 2 machines on ground, possibly 3 machines, and crunching through what's sitting there in some place between 12 and 18 months. If that is unsuitable, we can add more machines.
Would you need a larger footprint area then to place these machines?
It would be 40 feet by 100 feet for each machine, and that unfortunately is being controlled by the DDESB. I can't. I get to some points where the DDESB is going to say, for the safety of the operator, and believe me, sir, we start from the beginning that the operator is safe, the environment is safe, we're not endangering anybody. I don't care if you come down and say it's got to be done tomorrow, turn up the dial, that's not going to happen. So DESB says I have to have certain setbacks and distances between operators and operations. So, yes, if I had 4 machines, it does take a larger footprint because I do have to start being concerned about standoffs and setbacks.
Are all these machines available then, or do you just have one, I understand, that's immediately available?
The one is immediately available. I can build, I just talked to the manufacturer before this week. We could actually have 4 built and delivered within 28 weeks.
28 weeks, okay. And the last question I think you answered, which was plans for handling the M6 from the bunkers, and that has to do with your ESS plan that I'm sure you'll need to file.
Right, exactly. And one of our team, not myself, not ourselves, that's not our expertise, but we have assembled a team that does have that expertise. And I would, but that, you're right, sir, that all becomes part of the DDSB safety plan.
Thank you.
Okay, let's take the last question quickly, and we'll sign off.
And your last question comes from the line of Karen Price.
Yes, sir. We've reviewed the research, development, demonstration permit that you have through Utah. Can you tell me, do you have any other permits in place, or is it just the RD&D permit?
We had the RD&D permit, and at the end of the contract, the federal government did not. That contract was completed. The appropriation cycle did not allow for further funding, so that is a machine that is currently and uniquely available. But as part of our discussions, even as short as a month ago, we talked with UDAC. They were very acceptance of the data that we collected during the RADA of the SEMS, and are quite willing to accept a permit application, and their feeling is that it would take another 143 days in their state to get a full-up permit to construct, followed by permit to operate based on that. And if you would like to, I can get you I just don't have them in front of my eyes right now, the names of the gentlemen out at UDAC if you'd wish to contact them.
Yes, sir, we would like that information. And also, can you tell me what was the highest feed rates that was handled for propellant through that RD&D permit?
Through propellant, I'd have to go back and calculate because the propellants were being carried through as parts of munition. I can tell you that we were feeding 500 pounds an hour of RDX through full-up explosive, and I understand it's not the same as propellant, but it gives you an indication. I put it out as an indication that we can handle bulk energetic. I will calculate that number and get it to you with the understanding that it was part of a larger munitions weight load. And if you've seen our RD&D permit, you understand that we were limited to 550 pounds an hour loading by permit because of their concerns of lead and the RD&D permit, not because of what the machine is capable of. The machine could have run about 3 times heavier loaded than the permit allowed, but UDAC, their RD&D group or permit language felt comfortable at the 550, not the full capability of the machine.
Okay. One more question. Do you have a written response from EPA indicating that your system is not defined as incineration and whether you do not have to meet the requirements of 40 CFR 63 subpart EEE?
Yes, ma'am. We have that, and it was signed under the guidance of the EPA's General Counsel. And again, Doug, if you would be the point of contact, I will make sure that a scanned copy of that letter is delivered.
Appreciate that. Thank you.
Thank you.
So thank you, everybody, and appreciate your patience. I'm sorry, was somebody else trying to speak? Thanks a lot. And so we're done for today. We had our 2 today. We do have 7 confirmed for tomorrow, beginning at 10:30 Central Time. I will send the updated list. There's also one more, the General Atomics, that we're trying to schedule, and we'll let you know how that goes. So look for that email later this afternoon, and we'll talk with you all tomorrow. If you ask any questions of any of these vendors, it would be helpful if you CC'd me on emails. That way I'll also see the response, and I can help coordinate making sure everybody gets the information. So have a good day. We'll talk to you tomorrow.
This concludes today's conference call. You may now disconnect your lines.